an interesting consequence of diffraction that we can study now that we have done single slit diffraction is beam spreading. So we can think of what we made as a beam. Okay, so we had a couple of opaque regions with a slit, and we had a plane wave go through. And right as it went through, it made what's called a top hat beam, where the irradiance, if we were to plot the irradiance as a function of height, it'd be 0, 0, 0, 0, and then go up and be a fairly sharp in the near field value, and then 0, 0, 0 again. The diffraction doesn't occur until you get farther away. So we created a top hat beam, but then we calculated what diffraction does when you get far away on the screen, and we said, oh, well, we get this, sinc squared function like this, right? So if you wanted to think about sort of what is the width of this beam, you'd say, well, it's kind of here, and you might say the width is out to the first minima. So if we consider this central lobe of the sinc squared function, the beam, and most of the power is in that central lobe, there's not as much out there, then you might say the beam looks kind of like that. And then if you were to plot on a screen further away, sure enough, it would continue to spread like this. So if we plot those along straight, that's where the minima would be. And we know that's true because of the expression that we wrote. It was sinc squared of beta, and beta was proportional to sine theta, and for small angles, sine theta is proportional to theta, and for small angles, then theta is proportional to the height, right? So as you go further out, it spreads out, okay? So to find the width of the beam, from the minima of sinc squared beta. Well, you don't really have to deal with sinc squared beta. You know sinc squared beta is sine squared beta over beta squared. And you know the minima are going to occur when sine squared beta is 0, which is going to occur when sine beta is 0. So, so they actually, when sine beta equals 0, except for the value at 0, right? So usually sine is 0 at 0, and then pi, and then 0 again, and pi, and 3 pi, etc. But that's not the case for the 0. So you just have to ignore that first 0. So then you get that basically it's true when beta equals m times pi for m equals plus or minus 1, plus minus 2, plus minus 3, etc. So it's just a way to avoid m equals 0. And then you say, well, what was beta? It was 1/2 kb sine theta. 1/2 kb sine theta. Well, we're going to have a 0 when that equals m pi. And then you start getting rid of stuff. This is 2 pi over lambda, right? So those go away, and those go away. And then let's see, you could, what do we want to solve this for? We want to solve it for sine theta, right? So sine theta equals what? M lambda over b. That's where you'll have the minima. Right? And if you want the first minima, you just let m equal 1. Right? So when first minima sine theta equals lambda over b. And if you really want to think about beam spreading, so the theta we're talking about now is not our diffraction theta necessarily, it's a theta to the first, oh no, it is our diffraction theta, sorry. It's the angle down, right? But if you want to think about really the spread of the beam, you can say, well, for small angles, sine theta is the height over that r. We can call it big R. So that would be y along the screen. I haven't used y yet, right? Yeah. Over r, so it'd be where y is over r, so r times lambda over b. Okay? So the farther out you go, the higher the minima is going to be, right? So the longer we make r, the higher it's going to be, right? So if this is r. So that's showing you that it is spreading out essentially linearly as long as we keep the angles fairly small. It also shows you that when b gets small, the spread gets really big, right? So I call this delta y if I want. So this is sort of the spread of the beam. Right, so when we get a nice narrow slit, it spreads out. When we open the slit, it comes back down. So the narrower the slit, the stronger the diffraction effect. So what this means is if you make a top hat beam by just sending a plane wave through a slit, you're never really going to get a collimated beam. Right? It'll never actually be a nice tight beam because light turns a corner. Now you might say, fine, I won't make a top hat beam, I'll use a laser beam. Right? Lasers, we know, are highly collimated. Well, a laser beam is actually a Gaussian beam. So we call this a top hat if, for a Gaussian beam, it's the same idea. If we plot the irradiance versus position, it's just that the shape of the beam is a Gaussian rather than a sharp top hat. Okay? But even though it's not a sharp top hat, you still have diffraction effects. Even a Gaussian beam will spread out as it goes. Okay? So beam spreading is not something that just kind of happens in a few cases. All beams spread. It is impossible to make a beam that's perfectly collimated forever. They'll all spread out. And it's because you always have more Haugens wavelets here than out here, and they interfere, and they always produce this effect. Okay? So you think of a laser beam as highly collimated. It is highly collimated, but it's not really collimated forever. It seems that way because a top hat beam spreads instantly. A laser beam, the way a Gaussian beam spreads, it kind of stays together for a while and then it spreads out like that. And the distance over which it kind of stays together is proportional to the diameter of the beam divided by the wavelength of the light. And that's usually a big number, right? Usually we have sort of a millimeter or a few millimeter beam and we have half micron light. So it stays together for a long distance. But eventually it will spread out. And that's what I've set up here to show you. So here I've got our beam, which normally has sort of a 1 millimeter diameter. It's going all the way to the back of the lecture hall, bouncing off a mirror, and coming all the way back here. And here you can see it's more like a 2 centimeter diameter. Okay? This beam has not spread out because there's something wrong with the laser, or because I have a low quality mirror. This beam is spreading due to diffraction. You can see it's actually a very beautiful, perfect beam if you could get really close. I mean, it's really a very nice Gaussian beam. And it's spreading because of diffraction. So now I'm going to show you a little bit more convincingly. We'll turn the lights out and let you see the laser a little bit better and be able to see it spreading due to diffraction. All right. So now I'm going to try to make the beam visible. Up here, the up and down beams are so close you can't even tell them apart, really. But then eventually, now they're starting to separate a little bit. So the incident beam straight from the laser, the thin one, is on your left, and the reflected one is on your right. And now you can start to tell them apart. Now you can see this one, incident beam, still pretty sharp. And of course, the reflected beam is really falling apart. And the difference gets bigger as we get closer and closer. So here you can really see the difference. Let's see. And when I get all the way down here, huge difference. Very nice sharp laser beam on the incident, not much left on the reflection, and it's only because they've traveled so far. It has nothing to do with the quality of the beam, it only has to do with diffraction.